Okay, we talked about the conditions for cis-trans. There must be two different groups attached to the same carbon if you want to have cis or trans. And if the two groups attached to the same carbon, if they are the same, you cannot have cis or trans. We talked about priority groups for naming E or Z around carbon-carbon double bond. Then we talked about the heat of hydrogenations, which alkene is more stable based on the substitution number of the alkyl groups that you have around carbon-carbon double bond. Like if you have 3 alkyl group versus 1 alkyl group, if you have more number of alkyl groups, then the molecule is going to be more stable. And what does it mean if it's more stable? It means that it has less energy. So if it does go through, this one goes through the hydrogenation, it's going to release less energy because originally this compound contained less energy. There is a perfect comparison here. And why is a perfect comparison here? Because if you do hydrogenation here, by adding the 2 hydrogens to the carbon-carbon double bond, your products are exactly the same. So you have the same product here. So same product. See, these 2 products are the same. So is a point of reference. So it's going from what energy level to the product, or is coming for, if this is representing this compound, then the other compound is actually coming from higher energy level to the same energy level as the product. So both of them are the same here. So the energy level for the product is the same. So you have good comparison here. So the more substitutions around carbon-carbon double bond, it makes the molecule to be more stable. By experiments, they have found that delta H for the reaction is lower value, and that corresponds to stability of the molecule. Now, we are dealing with this concept more for the E2 mechanisms, or E1, E2 mechanisms. So we want to make sure that I want to make sure you understand the stability, the concept, why one is more stable, because of the number of the alkyl groups around carbon-carbon double bond. And how do they prove that is more stable is based on the reactions that they make these compounds go through reactions with different R groups around carbon-carbon double bond. They calculate delta H, and experimentally they find which one is more stable. We talked about physical property of these compounds compared to alkane. Alkene compared to alkane, they are more polar. They have dipole-dipole interaction, and as a result, the dipole-dipole interaction is going to have slightly is a stronger intermolecular force compared to van der Waals forces we have for alkane, and as a result, is going to be higher boiling point, higher melting point for the for alkene compared to alkane with comparable or same number of carbons. So how do we synthesize the alkenes? That's another concept. So we have physical property, structure, elements of unsaturation, which was new for this chapter, and preparation for these compounds, and reactions for this for these family of alkenes. So today we're just looking at the preparation, because we talked about everything else yesterday. So we talk about preparation today for E2 mechanism, the hydrohalogenations. We learned about these reactions in chapter 6. And we are going to continue here as a review and also emphasize on this structure. Like for E2 mechanism, as we talked about yesterday also, it has to be anti-coplanar. What does it mean, anti-coplanar? If the halide is leaving from one carbon, hydrogen is leaving from adjacent carbon. The hydrogen that is leaving from adjacent carbon or is being abstracted, that hydrogen is going to be in the opposite side of the halide that is leaving. The explanation for that is this halide is leaving is electron rich. The base which is coming to remove the hydrogen also is electron rich. They don't want to be on their neighborhood. So if the bromine is leaving is in this neighborhood, the base should be in the opposite side for easier access. So anti-coplanar, remember, for E2 mechanisms. If you use you need to also know the bulky bases. For the bulky bases, the advantage of bulky base is that it's going to slow down the SN2 type reactions. It's a strong base. It can go through SN2 reaction also at the same time that it's going with E2. But if you have a bulky base, it would slow down the SN2, because for SN2, steric hindrance is going to be a problem. At the same time, if you have a bulky base, it's going to remove the hydrogen from the least substituted carbon that is less hindered. So it can take the elimination. It can do elimination, but not the substitutions. For the bulky base, when you use a bulky base, it's going to look for the easiest approach. So for easiest approach, what does it mean, easiest approach for bulky base? It means that is looking for hydrogen that is least substituted. The hydrogen that is least substituted in this molecule, if you're comparing compound A with compound B, bromine has to leave from this carbon, no choice. Then you have hydrogen on the carbon on the right side versus hydrogen on carbon on the left side. Your carbon on the right side is a primary carbon. Carbon on the left side is a secondary carbon. So your primary carbon is less hindered, less substituted, easier access. So if it's less substituted, how do we recognize it's less substituted? It has more number of hydrogens. It's attached to less number of carbons. So if any of those takes place, then we know that the hydrogen is less hindered or more accessible. So these hydrogens on the right side, they are more accessible because the carbon carrying those hydrogens are more is less hindered, contains or is attached to more number of hydrogens, versus the carbon on the left side, because it's a secondary carbon, that means it's attached to more number of carbon and less number of hydrogens. So what is the point of difference here in terms of the product? Because we are starting with the same reactant. Your compound A and compound B are the same reactant, exact same. Your reagent is a strong base. In both cases, you have a strong base. What we have down here, this is just the solvent, okay? The solvent, and this is solvent. Your strong base here is ethoxide. For B, the strong base is T-butoxide. Now, if you use a smaller base or less bulky base, is going to look for hydrogen that is more substituted, because if it removes the hydrogen that is coming from the carbon that is more substituted, as a result, you are going to get 1, 2, 3 alkyl group around carbon-carbon double bond. And that makes this product more stable. and you get higher percentage of that product. If you are using a bulky base, is looking for easier approach to the molecule. A bulky base is going to attack or abstract the hydrogen from carbon that is least substituted. And what is the advantages is that this is the more accessible, and your bulky base cannot go in and grab the hydrogen from this area because it's highly substituted. Then your final product is going to have less number of alkyl group around carbon-carbon double bond. So you have two alkyl group around carbon-carbon double bond. So this product here, when you have greater number of alkyl groups around carbon-carbon double bond, which normally that is the product that is going to form, is known as the safe product. That means is the major product whenever possible. If your strong base is not a bulky base, you will get safe product as the major product. The second reaction is exceptions to the safe product, and since it was presented by different scientists, is known as the Hofmann product. So when do you get Hofmann product, and what does it mean that you have Hofmann product? A Hofmann product is a product that the carbon-carbon double bond it has lower number of alkyl groups in the molecule. So when you have two choice, hydrogen that is least substituted from least substituted carbon, you have a hydrogen from more substituted carbon. If the more substituted carbon is abstracted, you will get more stable product and is known as the safe product. If least substituted hydrogen is abstracted, you would get Hofmann product. Hofmann product is not the preferred product, but if that's what you want to make, like if you want to make 1-butene, and that's the only product that someone asks you to make, then you cannot say, because 2-butene is more stable than 1-butene, I'm going to make 2-butene, because you're not going to make a decision based on the stability of the product. You're going to make a decision and propose a method for preparation based on what is needed to be synthesized. So if you were going to make 1-butene, you cannot use a smaller base. So you have to use the you have to take the Hofmann product, and in order to make Hofmann product, all you have to do, change your base, use the bulky base to get a Hofmann product. With the elimination, as we talked about already, is anti-coplanar. So you get the bromine leaving from one side and the hydrogen leaving from the opposite side. So you could get either only cis or only trans product. For cyclohexane, and it was a good question earlier that why we are concerned about cyclohexane and the stability of the cyclohexane so much, because that is the most stable cycloalkane. We have two stable cycloalkane, cyclopentane and cyclohexane, and that's why we are talking about those two more than anything else. So when cyclohexane goes through elimination, the Br must be, or halide, it must be on the axial position, not the equatorial position. So Br must be abstracted from the axial position, and as a result, the hydrogen that is coming from the adjacent carbon also must be abstracted from the axial position. Why axial position? Because it has to be anti-coplanar. And if the Br is on the axial position on carbon 1, hydrogen would be on axial position on carbon 2. So on this carbon also, the hydrogen is going to be in axial position. So you can, if the bromine has to be in the axial position, the hydrogen that is abstracted also is going to be in axial position. Now, it's not going to make a difference in this case. You won't see the difference in product, formation of the product, because this hydrogen and these hydrogens are not much of a difference. There's not much of a difference between the two. Now, if you had a different hydrogen, or you had isotope of the hydrogen, then you could see the difference. So the bromine is leaving from here. This bromine must be in axial position, right? This bromine must be in axial. That is the starting point. If the bromine is in axial position, then this hydrogen is in equatorial position. If bromine is in axial position and coming toward you, what about this hydrogen? Is this axial or equatorial? This hydrogen? Okay. If this bromine is axial as coming toward you, the hydrogen, when you are moving clockwise, this hydrogen that I have blue mark around it, is also coming toward you. So if on carbon 1 axial is coming toward you, then carbon 2, the axial has to go away from you. So basically, this must be axial, bromine must be axial, and then you come down here, hydrogen is equatorial, and D is axial. And you need to know this from prior chapters. If the group that is coming toward you is axial position, on the adjacent carbon, the group that is going away from you, that is going to be axial. If it's coming toward you, it's going to be equatorial. So basically, you go one more time, you say axial up, axial down, axial up, axial down, axial up, axial down. Okay, axial up, axial down, and then you are going to get the practice it so you can get the concept, or you are using again in future chapters also. So if D is abstracted, you are going to get the product is going to be, if D is abstracted, you don't see the deuterium on the product, you have the hydrogen. So that is what is observed. So what you don't see is that hydrogen being abstracted. So this is a proof that the hydrogen that is being abstracted is coming from the axial position, anti-coplanar. So one supports the other. Either you know that it must be anti-coplanar, or you do this experiment and say, because, okay, you do this experiment and then say this is the final product, and since this is the final product, then we know that this is going to be come from the anti-coplanar, and then this is going to be abstracted. Now, would it take the hydrogen most hindered or the least hindered? It depends on the structure of the base that you have. So you're going to get the, if you use a bulky base, is going to come and abstract this hydrogen. So it has to be trans-diaxial. So it's going to be trans-diaxial. Why is not coming this the hydrogen on the other side, this hydrogen is, if this hydrogen is okay, let me answer your question first, that how do we know we are using bulky base or not? If you would have used bulky base, in this case, this would be the only product based on the Hofmann and Saysoff product. But in this case, the base that you're using is not a bulky base. A bulky base, we had 2 slides prior to this. We looked at the bulky bases, and if you have like T-butoxide, or is like actually more than 4 carbon in the 4 carbon or higher in your, or combination of carbon nitrogen, those were some of the examples that we saw for the bulky bases. So this base is not bulky, and since it's not bulky, is going to actually prove that you must get diaxial removal. So bromine is in the axial position. This bromine is in axial position. What about this hydrogen? Is that axial or equatorial? This hydrogen, is it axial or equatorial? That's equatorial, and thank you. That's equatorial because this has to be axial. So we already know that this is going to be axial and this is equatorial. Now, out of these two, D is also axial. In this adjacent carbon, if you move up counterclockwise, CH3 is in the axial position. For elimination is a dehydrohalogenation. You are removing halogen and you are removing hydrogen. So you're not removing CH3, which is in the axial position. So you have to go clockwise. You have choice of hydrogen in the equatorial or D in the axial. So if the axial equatorial was not a question, this product would have been better product because you get more alkyl group, more carbon around the CC double bond. But since diaxial position is important for cyclohexane, if bromine is coming from axial, the hydrogen must come from the axial. That's why this product is the observed product. So since this product is observed product, it's going to prove that this diaxial is a big deal, and the abstraction of hydrogen should come from the axial position, because bromine is in the axial position. And bromine, if it's in the equatorial position, it has to change to axial position before it's being abstracted. For vicinal dibromide, you would also end up with formation of the alkene, and right now just know that it's anti-coplanar, and then we look at the mechanism in next chapter, chapter 8. But what you need to know for now is what is the reagent that you could use. You have choice of 2 reagents, either zinc in acetic acid or sodium iodide in acetone. So when you are looking for, when you study chemical reaction, there are 3 things you need to know. And exam question or quiz question is coming from 2 information of the 2 or 3 information is given to you, and the last one is asked. You have your reactant, your reagent, and your product. What is your reactant in this case is a dibromo compound. So you have dibromo diphenylethane, and then your product is alkene. So is a dihalide, it's a vicinal dihalide, and the product, so you have your reactant and you have your product. You must memorize your reagent. So if you don't have a reagent, this reaction is not going to happen on its own. Some of the reactions, it requires a catalyst. So you also need to know, what does it require a catalyst or it doesn't require a catalyst. Why do we need a catalyst for some reactions? Because those reactions are not going to go spontaneous without bringing catalyst, because what catalyst does, catalyst is going to lower the activation energy. And if you don't have the catalyst, your reaction, the heat for the reaction is not enough. Your reaction is going to be highly endothermic. It's not going to happen. So you have to use a catalyst. So if the reaction requires catalyst, you must memorize the catalyst also. So you must memorize the reagent, and you need to know your reactant, what's your product. When you study the reaction, you want to know the mechanism of the reaction and what type of structure, like how the structure of the product is affected. So for dehalogenation and dehydrohalogenation, the abstraction is anti-coplanar. So it's coming from the opposite side. If it's coming from opposite side, that means your product is going to be more of a trans than the cis in this case. Your reagents, sodium iodide or zinc in acetic acid. So that's two methods for preparation. No, there was no catalyst in this case. We didn't have to use a catalyst. It was just but I mentioned that because I was talking about what is important for you to know when you're writing a chemical reaction. You have to write your reactant, you have to write your product, you have to write your reagent, and sometimes your reagent, like you have a nucleophile, but you also have to have a catalyst. And if you don't have the catalyst, that reaction is not going to be taking place. And catalyst is going to add another step to the reaction, because basically what it does, it breaks down the activation energy to like a smaller activation energy. That's what the effect of catalyst is. Other method for preparation of alkene was the elimination reaction via E1. For E1, because carbocation forms, then tertiary is going to go faster than secondary. For E1, you have more stable carbocation. At the same time, there is a chance for rearrangement. So anytime you talk about E1 or SN1, consider the possibility of rearrangement because you have intermediate. For E2 and SN2, you do not have intermediate. And if you don't have intermediate, there is no rearrangement. For E1 elimination, you start with alkyl halide and you end up with alkene. So your reactant is alkyl halide. I repeat this too often. It's like if it was me, I would have memorized it already. So I repeat it because I want you to memorize and get the idea when you are studying the reaction is not just knowing the name, or it's necessary to know the name. At the same time, you need to know what's your reactant, what's your product, because that's going to help you to remember for your exams like much easier. Your reactant is alkyl halide, your product is alkene. What's your reagent? Your reagent is going to be a strong base because you are doing a elimination reaction. So you must have a good leaving group, a tertiary carbocation for E1 or secondary carbocation, and a good leaving group also. For E1 mechanisms, I take it back, your base doesn't have to be a strong base because carbocation forms first. So weak nucleophile, it's okay for E1. For E2, you need a strong base. And the SN1, it usually could be a byproduct, but to avoid SN1, you can increase the temperature because elimination, it can be favored over substitutions if you are increasing the temperature for high temperature. Dehydration of alcohol. For dehydration of alcohol, your reactant is alcohol, your product is going to be alkene. In dehydration, you are removing OH, and you are removing H, just like the dehydrohalogenation. You remove Br and you remove H. OH from one carbon and hydrogen from adjacent carbon. Now, for OH, can you tell me if OH is a good leaving group? Is it a strong base? Is it a weak base? Is it a good leaving group or not so good leaving group? It's a strong base. And if it's a strong base, it cannot be good leaving group, right? Bad leaving group. If it's a strong base, strong bases are, because they are very reactive, they always want to look for another like positive center, because a strong base is looking for H plus to combine. So it's not going to be good leaving group. OH is not good leaving group. This is something that you have to say maybe 5-6 times over and over. OH is not good leaving group. OR is not good leaving group. Alkoxide is not good leaving group. OH is not good leaving group. And the reason for that, because this is a conjugate to H2O. H2O is very weak acid. So conjugate base is going to be very strong base. So it's a weak acid, and then you have a strong base. Yes. Is a strong nucleophile, strong base, but is better base than the nucleophile. It's not a good nucleophile because of the electronegativity of oxygen. I guess the OR also is not very is not a good leaving group because it's coming from let's say you have a CH3OH. CH3OH is a weak acid. Alcohols are not strong acids, otherwise you wouldn't be able to drink them, right? Alcohol is a very weak acid, and alkoxide, after losing hydrogen, it becomes very strong base. So it's not a good leaving group. So because OH is not good leaving group, and we want to make sure that OH leaves because we want to do dehydration of alcohol, how are we going to do this? We have to bring catalyst in this case. The catalyst that is going to do this, help this reaction, is a H plus coming from a strong acid. And the strong acid that is used in here in this reaction is a sulfuric acid, like concentrated sulfuric acid. You can't use dilute sulfuric acid at all. So it has to be concentrated sulfuric acid. What it does, acid provides H plus. And when the H plus is released, it's going to come to this molecule of alcohol and say, where is the best place for me to sit? That H plus, the best place for the H plus to come in is going to be this oxygen, because you see the pair of unshared electrons. When you draw the arrow, you should always draw the arrow from electron rich to electron poor. So H plus is electron poor. The oxygen has 4 electrons here. So we know that this is coming, the hydrogen is going to sit on the oxygen, because oxygen is the place in this whole molecule, because none of the carbon have, none of the carbons has the pair of unshared electron, and hydrogen, it doesn't accept another H plus because it doesn't have extra electrons. So this H plus is going to form bond with the oxygen. So what do you have here? Instead of the OH, now you have OH2. OH2 with the plus charge. If you rearrange this, isn't that same thing as H2O? Now, H2O is a good leaving group. So this is a bad leaving group. OH is a bad leaving group. You protonate that. Now it changes to H2O, a good leaving group. Okay, good leaving group. It changes to H2O. What do you remember from OH2 plus? when oxygen is forced to carry the plus charge. This is the case here. It makes the molecule very unstable because oxygen is highly electronegative, doesn't want to have that plus charge on it. What is the solution? I suggest two solutions before, and I said we will see this again. What are the two solutions? The solution is the two options. You remove H2O. If you remove H2O, the plus charge is going to go to the carbon. The other choice would have been to remove the H plus with the plus charge here. Those are the two options. Which option is the choice of the choice today for this reaction is removing H2O, because if you remove H plus, you go to the reactant. Going to reactant is not going to create the product. So we are not going to go back to the first square where we started with. We don't want to get the alcohol, we want to get alkene. So we remove H2O. So H2O is removed. When H2O is removed, carbocation forms. So you have your carbocation. When you have the carbocation, then the next step of the reaction is going to be fast step because carbocation has formed already, and base is going to abstract one hydrogen from adjacent carbon. We saw this in elimination reaction also in E1. After the leaving group leaves, the only two choices, again, you have two choices and you have to be wise to pick your choice based on what product they told you to prepare. Is going to be your professor telling you what product to make, or is going to be your boss when you are working in a lab to tell you what product to make, and the only choice you have to come up with the best method to make the product with highest % yield and the least cost and the least time, because time also is money. You don't have a choice of changing the product. So if you want to make the product to change to alkene, you cannot say, okay, if I bring a nucleophile here, I can stabilize this carbocation, because you have seen that in SN1, SN2 reaction. If you have a plus charge on carbon, you can bring a nucleophile with a negative charge, it cancels this. But that is going to give you byproduct. We are trying to avoid byproducts. So we have to remove the hydrogen. So we bring a base, hydrogen from the adjacent carbon is going to be removed. You are removing OH, you are removing H, your product is going to be alkene. So when you remove OH, you remove the 2 electrons, okay? When you remove the OH, you are removing OH with both electrons. When you remove H, you remove H without any electrons. So if you don't remove the electrons, this pair of electrons, it drops in, and when it drops in, it's going to give you carbon-carbon double bond. Is the anticoplanar a question for this type of reaction, for dehydration of alcohol? Does it have to be anticoplanar or not? Idea of anticoplanar is only for E2 mechanisms. For E1 mechanism, because you have carbocation forming already, you have intermediate, so the anticoplanar is not a question for E1. I just want to emphasize on that. So when you are dealing with anticoplanar, that means you are dealing with the E2 mechanism, not E1 mechanism. Okay. So what are the steps in dehydration of alcohol? Step 1, protonation of OH. OH is not a good leaving group. You have to protonate the OH to change it to better leaving group. What do you need to protonate the OH? You need acid. So you bring the acid. When you draw the arrow again from electron rich to electron poor, So you make the oxygen to gain the H plus, it changes to H2O. Plus charge on H2O is a disaster. So I just emphasize on that OH or H2O. Anytime you have plus charge on oxygen, it's going to make the molecule very uncomfortable. That means it gives a lot of energy, so it's very reactive, unstable. In order to stabilize it, you are going to remove the plus charge. How can you remove the plus charge? Two choices: remove the H plus or remove H2O. The only benefit that I see here to move to next step is to remove the H2O, and when you remove the H2O, you end up with carbocation. So your step one, protonation of OH. Step two, formation of carbocation. Step three, abstraction of hydrogen from adjacent carbon. So you remove the hydrogen from adjacent carbon. When you remove the hydrogen, electrons are not removed with the hydrogen. Those electrons are going to drop in, and you get your product of alkene. So when you study your reaction step by step, basically you are studying mechanism for the reaction. So if you're asked for mechanism for dehydration of alcohol, you have to bring the steps one step at a time. So you have to draw this whole reaction. First, you say step one is going to be protonation of the alcohol or OH. Step two, formation of carbocation, and step three is going to be is the elimination reaction. Yes, is the elimination reaction, and it's the formation of carbocation. And since it's formation of carbocation, it's going to be E1 mechanisms, and the possibility of rearrangement as well. Other methods for preparation of alkene, which we saw that in chapter 3. As a reaction for alkane, we said the cracking of alkane. So if you crack alkane that has 18 carbon, with 18 carbon, you are going to get how many hydrogens? That's going to be 36, right? 38 hydrogens. When you cut down in 2 molecules, so if I do symmetrical, so it's going to be C9 and C9. If I satisfy the first one with hydrogens, I take 20 hydrogen to satisfy the first one to make an alkane, and how many hydrogen is left for the second one is going to be 18. So if this is an alkane, it's going to be alkene. And now we can mention to this as one of the preparation method for alkene is the cracking when you are not providing any hydrogen. If you provide hydrogen, both of them would change to alkane. So we learned about naming alkenes. We learned about preparation of alkenes. We learned about Hofmann and Saycev product. We learned about E2 mechanism with anti-coplanar abstraction of the leaving group and the hydrogen from adjacent carbon. And the halogenation of Vicinal bromides. These are methods for preparation of alkenes. Any questions? Questions? Chapter 7 is going to be today. I'm going to make it available today, later, and it's going to run to tomorrow. So if you want to change it if you want to take it today or you take it tomorrow, because on the schedule is today, right? And the schedule is today. And the vicinal bromide is E2. Bulky base. Sure. We had the examples of the bulky base. Yeah. These are the examples for bulky base. Tibbutoxide is the smallest one. So you have the triethylamine. Amines is like a nitrogen, carbon-nitrogen bond is going to make the molecule to be amine. So nitrogen has pair of unshared electron. And that pair of unshared electron in nitrogen, it makes the amine to act like a base. So the alkyl groups that you have around the nitrogen, they are electron donor. That's why if you have a tertiary hydrocarbon, is going to be more stable than secondary, more stable than primary, because these groups are giving electrons. So because these groups are electron donor group around the nitrogen, they give electron to nitrogen. Nitrogen also has pair of unshared electrons on its own, and it's going to give more basic property to the nitrogen, so nitrogen can actually share the pair of electrons, or can accept protons, or can abstract protons. So it's acting as a base. So if you are using a bulky base, you have these are the examples. The easiest one to remember for you is this one. If it's not a multiple choice questions, like if you are trying to write down the bulky base, this is the easiest one to remember. But these you have to recognize it. Recognize that if you have a tertiary amine or secondary amine, that you have two bulky alkyl group attached to it, it can act as a bulky base. Bulky, yes, bulky base. And when do you need the bulky base? Whenever you want to get the hydrogen from least substituted carbon. Okay? If you want to take the hydrogen from least substituted carbon, you would use bulky base. Otherwise, you don't have to use bulky base. You're going to use just a less bulky base, or not bulky base, like a methoxide, like a toxide. Why would you use tibbutoxide if you can use the methoxide? And so methoxide is a strong base, is not bulky, is going to remove the hydrogen from more substituted carbon, because it's going to give you more substituted alkene. That's the benefit of it, to get more substituted alkene. So bulky base is only used if you have to make primary or terminal alkene. That means the CC bond is on between carbon number 1 and 2, or looking at the molecule, least substituted alkene in general. So it's not always the one, the carbon-carbon double bond between carbon 1 and 2. Okay, any other questions? Okay. I don't have the quiz ready, so I don't want to say soon, and then you know, not to make it available, not to be able to publish it soon. So it's going to take me time, at least like to 2 o'clock today, to make the quiz available. So the later I make it available, then I give you more time from the other, for ending the quiz. I'm pulling up chapter 8, and there were a couple questions that I missed it. So I'm going to make this honor lock also. Please go over the tutorial for the honor lock, how it works. There is a folder for honor lock, and there was so make sure that you can take the test with the honor lock. And piece of paper during the quiz to help answer questions. Yes, you can use 2 scratch papers. Scratch papers, you can use up to 2 of them. It's basically proctored. It's like you are taking exam when someone is in the room. So it's recorded, and I am expected and I am obligated to go over and look at it. At the same time, there are people who are monitoring you while you are taking the test. They are watching, and if there is like activities that it's flagged right away, and then they look and they can stop your test. So it's both ways. So it's going to be, but don't out the honor lock. Take your quiz. That's all. Yeah. Take your quiz like you were taking the quiz. You study the chapter, then you take the quiz. If you worry about the honor lock, if you worry about the browser lockdown and all that, it is going to be hard to concentrate on the test. You're not expecting to copy the answers. You're expected to know the answers. So that's all you do. You study before you take the test, and then you take the test with confidence, and there should be no problem. The only thing is that they have to make sure that you are using you are taking the test. So they take a picture, they check your ID. It's necessary for online courses to validate, to make sure that there is something as a backup. Nobody, when you transfer your grade, nobody can question that, well, you take the quiz or the test online. You did because